Okay, we're going to resume here now. And so once we have the quantity relationships, we can do it in different ways. But the most common way we're going to use these are in terms of moles. Usually we don't work with individual molecules typically, or a few molecules like this. And so the way I would read this is, rather than 4 molecules of ammonia, I'd read this as 4 moles of ammonia. You know, 4 moles. Moles, we abbreviate MOL, drop the E, 4 moles of ammonium. And then I would need 5 moles of O2. And this is giving me 4 moles of NO and 6 moles of H2O. Now that's a huge number of molecules, because each mole is about 6 times 10 to the 23rd molecules. And so this is not by mass. You know, if we did this by mass, it'd be totally different. You know, for example, an O2 weighs 32 grams on average. So 5 times 32, I should be able to do that one, but I don't want to think too much. So 5 times 32 is 160. And so this is not grams. You know, if we're doing this in terms of grams, 5 moles of oxygen, a mole of oxygen weighs 32 grams. So 5 times 32 is 160 grams. So that would be 160 grams. And then ammonia, nitrogen weighs 1401, oxygen is 303. I mean, not oxygen, hydrogen. And so this is 1704 times 4. So 4 times 1704 is 6816. 6816. NO, nitrogen's 1401, oxygen's 16. And so 14 and 16 is 30. And so this would be 30.01 times 4. 30.01 times 4 is 120.04.
That's it. We can see nothing.
Oh, shoot. I can't see. I just shared it. I don't know what is wrong with that. Or I guess I should click the wrong screen. Okay, can you guys see it now?
Like the work that you did? No.
I guess I need to turn up my volume. All right. No, all right. Let me see. It's on the PowerPoint. I'm writing on the PowerPoint. That's weird. How about now? Can you see it now? Okay, how about now? Can you see it now?
Mm-mm.
Okay. Okay, do you see my screen now and the writing, the 4 moles NH3, 5 moles of O2? No, all right, something's wrong. Let me try something else. But do you see the PowerPoint? Is it on the PowerPoint? right, let me try writing now and see if you can see it. So, like I said, normally we don't work with individual molecules. Normally we work with huge numbers of molecules. So we do it in moles. Do you see that writing there, 4 moles? No. Oh, that's not going to work. Okay, I think I might have figured it out. Okay, we can see it now. Okay, good. All right, so what I had written up here is normally we don't do 4 molecules of NH3. When I see an equation like this, I see it in terms of mole ratios. And so the way I'd read this is 4 moles of ammonia, because it's very rare we work with, you know, only 4 molecules of ammonia. So 4 moles of ammonia, but it could happen, of course, you know. So this could be either 4 molecules of ammonia or 4 moles of ammonia. Typically it's 4 moles of ammonia. 5 moles of O2, 4 moles of NO, this should be NO, 6 moles of H2O, and that's what we got. So this is also not a gram or mass ratio. If this were mass ratio, we'd have 68.16 grams, you know, of ammonia, because each ammonia weighs 1704 grams per mole. So 14 times 1704 gives us 68.16. Each O2, mole of O2 weighs 32 grams. So 5 times 32 is 160 grams. NO, each NO weighs, nitrogen is 1401, oxygen is 16, so 30.01 times 4 would be 120.04 grams of NO. And 6 moles of water. Water is 1802, so 6 times 1802, what's that? So 6 times 18.02, oops. 108.12 grams. And so this should add up. 68 plus 160 is about 228. So 120 plus 108 would be about 128. So mass is conserved. You can see mass would be conserved in this. And so chemical reactions like this are, you know, particulate ratios or mole ratios, moles of particulate ratios. So we'll go with mole ratio. So chemical reactions like this are mole ratios. The formulas themselves are also mole ratios. You know, 1 mole of nitrogen for every 3 moles of hydrogen. And so the formulas show mole ratios and equations. Balance, it has to be balanced. Balanced chemical equations show mole ratios also. Once we have the mole ratios, then we can relate it. You know, if I have 4 moles of ammonia, I'm going to produce 6 moles of water. If I have 8 moles of ammonia, I'm going to produce 12 moles of water, you know, that kind of thing. So that's stoichiometry in a nutshell. So let's look at the next slide here. Oh, we have something called stoichiometry maps. The heart of the stoichiometry map is a mole-to-mole conversion. You know, moles of given, moles of desired. If I have 8 moles of whatever, you know, I might get 12 moles of something else. And so this is the mole-to-mole conversion. Mole-to-mole conversion is we need the mole ratio. The mole ratio is going to come from 2 sources. The mole ratio may come from the balanced chemical equation or the formula. It depends on what we're looking at, or formula. That's just possible. This is the particulate ratio, you know, so if I have like 4 molecules of ammonia, I'd have 6, you know, molecules of water, that kind of deal. And so the particulate ratio. Sometimes we'll use the particulate ratio or the molecule ratio or the atom ratio. Other times we'll use the mole ratio. Most of the time we're going to be using the mole ratio. So this is typically what we have. This is the heart of the stoichiometry map. This is the heart of the stoichiometry map. And then sometimes we'll add branches to it. Rather than going with moles, sometimes we'll go with grams. You know, let's say 100 grams of ammonia. You know, what I don't want to do is I don't want to do it this way. So I have the gram ratio here, but I don't want to get the gram ratio, have to calculate the gram ratios all the time. So instead of having to calculate the gram ratio or the mass ratio, this is the way we do it. The way we do stoichiometry is we start with the mass. Let's say I had 100 grams of ammonia. And then rather than going straight to grams of water, like I could do if I calculated the masses of everything, we'll convert it. In other words, we're going to start off with the mass and then convert it to moles. Well, mass to mole conversion, we just need the molar mass. You know, this is 1 over the molar mass. You know, in other words, flip over the molar mass. Molar mass is usually grams per mole. We'll just write it moles per gram. And then that means the mass units cancel out here. And so we'll use the molar mass here. Oops. We'll use the molar mass here, you know, for this step. And then what we do is we convert it to moles given. And then we'll use the mole ratio here for this step. And so we can go from moles of A to moles of B. And so basically, I just think of it this way. We're going from grams of A to moles of A. And then from moles of A to moles of B. Well, to go from moles of A to moles of B, we need the mole ratio. The mole ratio is given by the balanced chemical equation or the formula. Formula is tricky sometimes because atoms can end up in different compounds. And then we have the mole to mass conversion. So we'll go from moles of B to mass of B by using the molar mass. And so this is the molar mass here. And so these are the conversion factors we use for each step here, and then we end up with mass we wanted. And so essentially this is it. It's a grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. This is your standard stoichiometry problem or map. Standard stoichiometry problem. This is the most common one. We could have other branches too. So we could do this in particulate level, but you know, most of the time we aren't working with single molecules, that kind of stuff. And so most of the time we'll do this. This is for particulate, this is for moles. So we'll do moles. And so here's a grams of A to moles of A. But at moles of A, we can take another branch because from moles of A, we can go back to grams, or from moles of A, we can go to moles of B. Over here, this would be moles of B. Or we could go to the number of A particles, particles being molecules, formula units, or atoms. And so we can go from moles to particles if they're interested in how many particles. Or we can go from moles of B to grams of B, or moles of B to particles of B. And so there are additional branches here using Avogadro's number. You know, we could figure out the number of particles, or we could start off, you know, let's say I was given a million trillion molecules, and I can convert that to moles. And so, you know, you see these are double-headed arrows. We can go in any direction we want, you know, it's just using conversion factors. So we could start off with product, you know, go moles of B to, grams of B to moles of B, moles of B to moles of A, and work backwards to grams of A, work backwards to reactant. So you can go different variations of the stoichiometry map. So let's do a standard stoichiometry problem, except in this case, I'm going to use pounds rather than grams. And so 1 pound of methane, you know, 1 pound of methane, in stoichiometry, you know, methane contains carbon and hydrogen. So we can figure out 1 pound of methane contains how many pounds of carbon, how many pounds of hydrogen. That would be an example where we use a formula. Okay, right. Okay, can you do this? Can you tell me what the balanced chemical equation for methane combustion is? Now, the first thing is, what is methane? Methane is CH4, and it's normally a gas. And so for combustion, tell me what happens in combustion. So what, in other words, I want CH4 plus what? Blank. What is the blank? Not H2O, not energy. Combustion produces energy. And so we need methane plus something. Yeah, oxygen. The oxygen in the air is O2, you know, the diatomic or molecular oxygen. And so in combustion, we need the fuel. This is the fuel, which is the reducing agent. And we need the oxidizer. In this case, oxygen. Oxygen, again, is historically, this is why the term oxidation comes, because oxygen is the most common oxidizer we have around. Okay, this is going to produce blank plus blank. So what does it produce? Well, we have to assume complete combustion. You know, it could produce carbon monoxide. We don't want it to produce carbon monoxide, so we assume complete combustion always. And it's going to form CO2 plus blank. What's the other product of combustion? Yeah, H2O is correct. Yeah, it's got to be hydrogen something, and something is with the oxygen. There's only oxygen left after we use the carbon over here. Because we're going to put excess oxygen. Well, what's a minimum amount of oxygen we need for complete combustion? So the minimum amount is going to be based on balancing this. And so to balance, we have one carbon, 4 hydrogens. That means we need 2 waters. The 2 waters will give us 4 hydrogens and 2 oxygens. And so we have 2 oxygens from the CO2 plus 2 oxygens from the water. That gives us a total of 4 oxygens on the right side. And that means we need 2 O2s. If we have less than 2 O2s, we aren't going to get complete combustion. This is stoichiometry. We need, for every mole of methane, we need 2 moles of O2 gas. Now, there is a driving force for this. The driving force for this is we're going from stronger to weaker. And so in this case, methane is a stronger reducing agent. Oxygen is a stronger oxidizing agent. Then what? And so going backwards here, well, carbon is in +4, it has to go to -4. So this is going to be the oxidizing agent going backwards, CO2, and the reducing agent is going to be water going backwards. So oxygen versus CO2, what's a better oxidizing agent? Well, oxygen is. CO2 is a weaker oxidizing agent. And what's a better fuel, methane or water? Well, methane is a much better fuel or reducing agent than water. So this is going to be weaker. Here. Water is so weak, it's not normally considered a reducing agent, you know, fuel. But it can be, potentially be. Depends on the oxidizer. You need an awful powerful oxidizer to oxidize water. And there are some awfully powerful oxidizers that can oxidize water. So let's look at some calculations. If I have 1 pound of methane, how many pounds of oxygen are required? So calcs 1, how many pounds of oxygen? You know, I got to make sure I have enough oxygen. How many lbs of O2? Make sure I have enough oxygen to burn all that methane. And so I just do this using dimensional analysis. So we have 1 pound of methane. And for dimensional analysis, we want to get rid of pounds or pounds of methane. In this case, it will probably only get rid of pounds because we can go to 453.6 grams here for every 1 pound. So the pounds cancel. That leaves me with grams of methane. Well, if I have grams of methane, then I want to do a gram to mole conversion. because a mole-to-mole conversion is at the heart of the stoichiometry map. And so I need the molar mass of methane. Well, molar mass of methane, carbon's 1201, hydrogen's 404. So the molar mass of methane is 16.05 grams of methane per mole of methane. And so this is my grams of A to moles of A conversion. And then I do a mole to A to mole to B conversion. And so what I want to do is I want to do a methane to oxygen conversion. And there are 2 moles of oxygen according to the balanced chemical equation for every 1 mole of methane here. And so that gives me moles of oxygen. And then from moles of oxygen, I want to go to grams of oxygen. You know, there are 32.00 grams of O2 for every 1 mole of O2. And so that takes me to grams, but I don't want grams at the end, I want pounds. So I'm going to convert grams into pounds. And that is, there are, in every pound, there are 453.6 grams. And so the grams would cancel. And so then this is going to leave me with pounds of O2. The 453.6 here cancels the 453.6 here. And so let's just punch out the numbers. We punch out the numbers, I'm going to get 2 times 32 divided by 1605. That's it, I guess. 3.98 pounds. How many sig figs am I allowed? So it depends on the one. What do I mean by 1 pound? What I'm going to do is I'm going to call this hypothetical exact, you know, hypothetical. If it's hypothetical, you know, I didn't actually weigh it, you know, I'm just asking. Then I'm going to call this infinite sig figs. It's hypothetical, so let's call it infinite sig figs. And so that means I'm going to be allowed how many sig figs at the end? Well, this says how many sig figs. 453.6 has how many sig figs? 4, yeah. I'm going to be allowed 4 at the end. You probably can see that there. And so I'm going to get 3.9875. 3.9875 pounds, or 3.988 pounds of O2. And so if I have 3.988 pounds of O2, 3.988 pounds of O2, then that's enough. That's enough. If I have less than that, then I'm going to get incomplete combustion. If I have more than that, then that's okay. You know, it's okay to have more. How many pounds of CO2? Let's figure that out. So same setup. 1 pound of methane. Then we're going to do pound to gram conversion. So 453.6 grams for every 1 pound. And then we're going to do a gram to mole conversion here. So it's the same, you know, a mole of methane is 16.05 grams. This is different though, because we're not interested in oxygen. We already did the oxygen. We know how many pounds of oxygen. We need about 4 pounds of oxygen. So if I have 1 pound of methane, I need about 4 pounds of oxygen to react. What about CO2? Well, CO2 is what we call 1-to-1 mole ratio. And so for every 1 mole of CO2, I will need 1 mole of methane. Molar mass is next. Carbon's 1201, oxygen is 16 times 2 is 32 plus 12 is 44. 0.1 grams of CO2 for every 1 mole of CO2. And then again, we need to convert it into pounds. So 1 pound is equivalent to 453.6 grams. And the 453.6 grams cancel on both sides. So let's see how many pounds of CO2 are generated. And so that's going to be 44.01 divided by 16.05. Is that it? That's it. 2.7420. I'm allowed 4 sig figs, so I'll just call it 2.742 pounds. So about 2 3/4 pounds of CO2. So for every pound of methane, I generate about 2 3/4 pounds of carbon dioxide that's combusted. 3, how many pounds of water? H2O. How many pounds of water? Okay, let's figure that out here. So I got 1 pound of methane here, and then I'm going to go to grams, 453.6 grams per pound. And then I'm going to go to moles. 1 mole of methane is 16.05 grams. And then here is going to be different because I'm going to relate methane and water. And so I see it's 2 moles of water are produced for every 1 mole of methane that's combusted. So that takes us to moles of B. And we'll go moles of B to grams of B. So water's molar mass is 18.02 grams per mole. And then final conversion is to pounds. 1 pound is 453.6 grams. And so 453.6 cancels on both sides. So it's just 2 times 18.02 divided by 1605. I screwed that up. Try that again. 2 times 18.02 divided by 16.05. It's about 2 2/4 pounds. 2 and 2, 4, 5, 4 pounds of water, which equals 2.245 pounds of water. So altogether, I made about 5 pounds of product. So I should have started off with about 5 pounds of reactant. So 1 pound plus about 4 pounds. So I started off with about 5 pounds of reactant here, 1 pound of methane, 4 pounds of oxygen. And I end up with 5 pounds of product, 2 3/4 pounds of CO2 and 2 1/4 pounds of water. And so mass was conserved in this particular reaction. Okay. Well, that's kind of your standard stoichiometry. This would be a standard stoichiometry problem. You know, we're interested, most people are interested in this. For every pound of methane, we form about 2 3/4 pounds of CO2. Burn. Holy, okay. Not forget to record that, fortunately. Well, you know, that's called the theoretical yield. Like, you know, the theoretical yield is for every pound of methane that I burn, I'm in theory going to get 2 3/4 pounds of CO2. But sometimes it doesn't happen because we lose some, or maybe something or other thing happens and we don't end up with a full 2 3/4. We end up with less. This is like popcorn. This is popping popcorn here. And so how many popcorn seeds are there? 3, 6, 9, 12, 15, 18, 20. There are 20 seeds here. Well, if there are 20 popcorn kernels, I'll call them kernels, how many pieces of popcorn? We should get 20 pieces of popcorn here. So we got 3, 6, 9, 12, 15, 16. We only got 16. So we started off with 20 kernels, but we only got 16 popcorns. We should have gotten 20. And so this is what happens in chemistry. Sometimes you lose some, sometimes it doesn't react, you know, something happens to it. And in this case, we lost 4. 4 went unpopped. And so we have something called percent yield. In theory, we should have gotten 20. And so the percentage yield is equal to the what we call the actual yield over the theoretical yield times 100%. And so AY is the actual yield. AY equals the actual yield. The actual yield is 16 popcorns, you know, 16 popcorns. But TY is the theoretical yield. Theoretical yield. And the TY, we should have gotten 20 popcorns, not 16. So the percent yield is going to be the actual yield, 16, what we actually got, over what we're supposed to get. Theoretical yield is what you're supposed to get. We're supposed to get 20. We didn't for some reason. I don't know why these didn't pop. There's some reason. And we don't have to explain it. It just happens, and it happens, unfortunately. So what's that, 3/4? No, not 3/4. 1/8, 80%. Let's see. 16, yeah, 80% divided by 20. If I divide it by 2, it's 80%. And so only 80%, we only got 80% of what we're supposed to get. And so we call this an 80% yield. Yeah. So that happens in chemistry too. And so the theoretical yield is based on stoichiometry. You know, going grams to moles, moles to moles, moles to grams, that kind of thing. So this is based on stoichiometry. The actual yield is experimental, experimentally observed, yield. And the theoretical yield is based on stoichiometry, the yield based on stoichiometry. So let's say we burned a pound of methane. And so we'll do another example here. Let's say we burned 1 pound of methane. And we collected, let's say we collected 2.68 pounds, 2.68 pounds of CO2 was collected. I don't know what happened to the missing CO2. Some of it's missing because we should have 2 3/4 pounds. A little bit went missing, but you know, who knows what happened to it. But I do know that's my actual yield. This is my actual yield. And so we're going to calculate the percent yield here. The percent yield is going to be the actual yield, 2.68 pounds of CO2 over the theoretical yield. No, I erased it. I think the theoretical yield was 2.744 pounds of CO2. This is the stoichiometric amount. And so this is what we call the theoretical yield. Times 100%. And so let's calculate the percent yield for that. 2.754. Okay, thanks. Sorry. 2.754. So 2.68 was the amount actually obtained. 2.754 was the amount that was supposed to be attained times 100. And so the percent yield comes out here as 97.31% yield. So in other words, lost 2.7%, 2.69, lost 2.69% of the CO2. It could be lost because, or it could be never made. Like here, we didn't lose 4 pieces of popcorn. 4 pieces of popcorn never happened because here are the kernels here. So we don't know. It might not have been made, you know, or it might have been made and lost. You know, it could be end up somebody came and ate 4 pieces of popcorn. You know, could be different reasons. But this is an important number because in experimentation, oftentimes we don't get what we're supposed to get because we're not perfect. All right, the next topic is something called a limiting reactant. Limiting reactant is, let's say we don't have enough oxygen to react. You know, we needed 4 pounds of oxygen. Let's say we only had 2 pounds of oxygen. You know, well, we might get a different product, but, or, you know, something else. And so, let's see. And so let's take a look at this particular one. You know, this one, under these conditions, it prefers to form CO2. Looks like CO2. Here, we don't have enough oxygen to form. We have 3 carbon atoms. This will be in the gas phase. So they use some kind of laser or something to vaporize the gas. Carbon atoms. Carbon atoms don't like to be in the gas phase. Carbon atoms like to be together in the solid phase, you know, preferably graphite. And the next best one would be diamonds, then buckyballs and the others. And so they use some way of getting the carbons to go in the gas. And we have oxygen molecules here. If we want to form CO2, we don't have enough oxygens. You know, we have enough oxygens to react with 2 of the carbons. So we'll end up with 2 CO2s, but one of them is going to go unreacted. So it's a mismatch. And so in this mismatch here, you know, when everything's perfectly matched, we call it stoichiometric. You know, it's just right. But when things aren't matched, we call it limiting reactant. We still use stoichiometry calculations to figure it out. And we do it based on the smaller amount method. The smaller amount method would calculate, you know, if I had 3 carbons, how many CO2 should I get? Well, if I have 3 carbons, I should get 3 CO2s because each CO2 has 1 carbon. And then we look at, if I had 2 oxygens, how many CO2s would we get? Well, 2 oxygens, I could only form 2 CO2s. And so we pick the smaller amount. Well, the oxygen is a smaller amount. We don't have enough. Therefore, I'm only going to get 2 CO2s. And so the smaller amount is the theoretical yield. And so in this particular case here, the theoretical yield is only 2 CO2s. 2 CO2s is the theoretical yield. It's impossible to form 3 CO2s because I don't have enough oxygen. And so the theoretical yield is based on which one of these gives you a smaller amount of product here, like this. And so let's say if I had 4 pounds of oxygen, you know, let's go back to methane combustion, CH4 combustion. when I look at methane combustion, if I have 4 pounds of oxygen, I should be able to produce about 2 3/4 pounds of CO2, right? But let's say I have 4 pounds of oxygen and I only have half a pound of methane. Can I still form 2 3/4 pounds of CO2? And it turns out no, because I don't have enough methane. Methane is the limiting reagent. And so in this example here, you know, let's say we didn't know. And so the step one is to calculate the yield from each. Step one, calculate yield from each reactant. And so the first thing is we will calculate the yield from O2. So an example, I mean, in this case, we'll look at the yield of CO2 from 4 pounds of oxygen. So let's start off with 4 pounds of O2. And then what we're going to do is we're going to go from pounds to grams. And so 453.6 grams per pound. And then we're going to go from grams to moles. And so 1 mole of O2 weighs 32.00 grams. And then we're going to go from moles of O2 to moles of CO2, since I'm interested in CO2. And so for every mole of O2, looking at the balanced chemical equation, I'm going to have not enough here. Actually, probably the easiest is for every mole of methane, I need 2 moles of O2, rather than doing fractions. Do it that way. Half a mole of O2 would, 1 mole of O2 would give a half a mole of CH4. I don't want to put half a mole up there. And then finally, we're going to go to, actually, no, I don't want methane. Oops, I went the wrong direction, sorry. I want CO2. And so 2 moles of O2 for every 1 mole of CO2, and then go to grams of CO2, 44.01 grams of CO2 for every mole of CO2, and then from grams of CO2 to pounds of CO2. So a pound is equivalent to 453.6 grams. Okay, so this is going to be about 1 pound. I already know it because it's just close, but let's get it to a lot more sig figs. And so this is going to be 4 times 453.6. Oh, actually, I don't need 453.6 because they cancel. So 4, let me just clear that. 4 divided by 32 divided by 2 times 44.1. 2.75. 2.750. Actually, I'm allowed 4 sig figs. 2.7506 pounds of CO2. If I take 4 as exact, let's do that. Hypothetically exact. And so that's a yield of CO2 from 4 pounds of O2. Now let's calculate the yield, the same thing, the yield of CO2 from half a pound of methane. Again, this is a hypothetical problem. It's not actually measured, so we're just saying we have exactly half a pound. If this were measured, then it's impossible to get it exact. You know, how can you get exactly half a pound? It's impossible. And so we'll just go with 0.5 pounds, exactly hypothetical, of methane, and then convert that into grams, 453.6 grams per pound. And then to moles, 1 mole of methane weighs 16.05 grams. And then we want to go to CO2. We're interested in CO2. So it's going to be 1 mole of CO2 for every 1 mole of methane. And then grams of CO2, 44.01 grams of CO2 per mole of CO2. And then to pounds. And pound is 453.6 grams. All right, so let's do the calculation here. And that's going to be 0.5 divided by 1605 times 4401. 1.37. 1.3710 pounds of CO2. So if I burn all the methane, I get 1.37 pounds. If I react all the oxygen, I get 2.75 pounds. Well, it's impossible to get 2.75 pounds because once all the methane runs out, there's nothing else to burn. And so we call the smaller amount 1.371 pounds of CO2 is the theoretical yield. Theoretical yield, we'll call TY. Theoretical. And so, in other words, it's impossible to form this amount. The bigger amount is impossible. It's going to be the smaller amount here. We can't, this is the yield from carbon here is 3 CO2s, but we can't form 3 CO2s because we're limited by O2. Okay, so what we do then is we say that this is our limiting reagent, LR, to be limiting reagent. And this here is our excess reagent. And so we aren't going to burn, we're going to burn all the methane, but we aren't going to react all the oxygen. In fact, we're only going to react about 2 pounds of oxygen, and we're going to have about 2 pounds left over unreacted. And so that's excess, about 2 pounds of excess oxygen because, 4 pounds was enough to burn 1 pound of methane, but, I only have half a pound, which is half as much. So I only need half as much oxygen, which is about 2 pounds. Therefore, I'm going to have 2 pounds of excess reagent left over, but it can't react because there's no more methane to react it with. So it's a limiting reactant using smaller amount method. We have energy calculations as well, but here we're going to talk about the common energy units, the calories. Calories defined as the amount of heat, definition, is the amount of heat required to raise the temperature of 1 gram of water by 1 degree C. It's a calorie. Technically, it's a 4 degrees Celsius, but we aren't going to worry about that because it doesn't change a whole lot, So, 1 calorie per gram of water per degree C. This is called the specific heat of water. The joules defined by physics. It says a physics definition. It's the amount of energy required to lift 1 kilogram. 1 kg. So if I took a kilogram and I lifted it up by 1 meter, 1 kilogram by 1 meter against gravity, that would be 1 joule's worth of energy. So a joule is a kilogram going up a meter, fighting gravity. Gravity is 9.80, excuse me, meters per second. So you don't need to know the definition of the joule, but that's how it is. What's this one? This one is called the food calorie. Food calorie. A food calorie is equal to 1,000 chemical calories. And so the situation here is this here. Just 1 second. Right there. Okay. Okay, and so a food calorie, you know, let's say a chemical calorie is kind of small, you know, that's a small piece of energy. To raise the water, a gram of water by degree C doesn't cost you a huge amount of energy. But when you look at something like this, you know, my bar here, let's see how many calories this is. 170 calories. So I have a little coconut bar here. It's 170 calories. Well, it's actually 170,000 calories. But, you know, do you really want to be eating 170,000 calories? You know, if you go to McDonald's and have a 1 million calorie meal, you know, that's a lot of calories. And so that's too much. So we have a calorie. When you look at this calorie has a capital C. When you see a capital C, that's a food calorie. I don't know if you guys can see this here, but that. And so you'll see it here. If you take a look at this, that's capital C. And so really that's 25,000 calories, you know, but they dropped the 1,000, you know, and then do that. And so 1 food calorie is 1,000 calories, which is 1 kcal, you know, 1 kcal, which is equal to 1 kilocalorie. Yeah, the amount of energy required to lift 1 kilogram by 1 meter. That's what that's supposed to say. Amount of energy required to lift 1 kilogram by 1 meter against gravity. This one you need not know. This one you should know. So we can do conversions here. And one of them is a joule. You know, joule's not that much energy, really, also. You know, a joule is actually a smaller amount of energy than a calorie. And so when we do the relationship using physics, we can come up with the relationship here. Using physics, 1 calorie is equivalent to 4.184 joules. So joules actually about a quarter of a calorie, which is very, very small. And so 1 joule is about 0.25 or 1/4 of a calorie. And so this is 4 sig figs. This is the conversion factor that we use. It's common for this. So in chemical equations, what we have is we have two types of chemical equations. And we need the numbers here to show it. I didn't show it earlier, but let's look at methane combustion. Now, let's do a different color. Is this endothermic? You know, when you burn methane, do you have to add energy to it? So should I do plus energy, or does it produce energy? This is 2O2s. When I burn a pound, let's say I burn a pound of methane, you know, should I do? It turns out that it's exothermic. That is, when I burn a pound of methane, it's going to form, or actually, when I burn a mole of methane, you know, equations like this aren't mass ratios. Like, for example, some people might get confused. If I have 1 pound of methane, they might think I need 2 pounds of oxygen because it's a 1-to-2 ratio, but that's wrong. That's a mass ratio. This is not a mass ratio. This is a mole ratio. Masses are totally different. And so when I burn 1 pound of methane, I don't need 2 pounds of oxygen. I actually need 4 pounds of oxygen. Where did that number come from? Well, that came from the mole ratio, not the mass ratio. This is going to produce a mole of CO2 plus 2 moles of water to a liquid. This is a gas. This is at 25 degrees C. Now, this is exothermic. So what we say is it's plus energy here. Now, how much energy is it? Well, I can look that up, or you know, we can calculate it in Chem 1A. But let me look it up. So I put it on the next slide, I think. Check the next slide. 890.7 kilojoules. This amount of energy here is plus 890.7 kilojoules, you know, or 890,700 joules. That would be 890.7 kilojoules. The first thing is maybe how many calories is that? You know, how many calories is that? And so we can figure that out here by using the conversion factor here. Food calories, I'm not sure how much we're going to do with food calories. Okay, so we want to use this conversion factor right here. And so if I do that, I'm going to times this. Well, we want to get rid of kilojoules. So there are 1,000 joules for every kilojoule. Kilo is 1,000 times 1 calorie for every 4.184 joules. So that'll give me the number of calories. So let's calculate how many calories that is. 890.7 times 1,000 divided by 4.184. 212,882. 212,882 calories. Or 212.8. How many sig figs am I allowed? 4.88 kilocalories, which is going to equal 212.9 kilocalories. Or this would be 212.9 capital C calories. So it would be about 213 food calories. So a pound of methane, what would this is 170 calories. And so a pound of methane would contain more energy than this bar does. Unfortunately, you can't eat methane. If we could eat methane, then I could get calories from methane. But there are lots of things that eat methane, though. And there's bacteria that love to eat methane, you know. Okay, so that's it. Now, there are different ways of expressing this. We call this number delta H. Delta H. Delta H is the amount of energy or heat, we say heat of reaction. Let me write that up here. Delta H equals heat of reaction. And actually, it's time for break. So it's break time. So let's go ahead and we're going to take a break for 15. Let me see. Is that what the message is here? Yep. Okay, break time. So let's take a break for a little over 15. I'm gonna go grab something. And so a little over 15, we'll be back, okay? All right, so let me pause the recording here. All right, so let's continue where we left off here. Let me see, am I sharing? Maybe I'm sharing. Okay, let's clean it up a little bit here. Oh, shoot. I guess I just lost all my annotations. Let me see. This still had it in there? No. All right. That's all right. Okay. So 8 minus 890.7. So in the chemical equation, there are different ways, you know. What we're talking about is delta H. Delta is change and H is enthalpy. And so this is delta H is equal to the change in enthalpy. Enthalpy is energy also, but there's certain restrictions on the energy here, and that's why we get another name rather than calling it energy. These restrictions are discussed in Chem 4. I'm not really going to talk about them here because it's beyond the scope of the class, but you know, think of this as energy. And a lot of people think of this as heat energy, but it's not always heat. You know, it could be work energy as well. And so when people look at delta H, they just simply say it's heat of reaction. That is, if you converted all this energy into heat, that's how much heat you get. And so oftentimes when we burn methane, we just use that to heat things up. And so if we convert that all into heat, that's how much heat we'd get. But you don't have to convert it all into heat. You can use some of that energy to do work. If you do work, you're going to get less heat, because if you remember, you know, the energy is going to equal the amount of heat you get plus the amount of work you do, you know. And so actually doing and getting are two different things. You know, when you do something, you're expending energy. When you get it, you're gaining energy. So if I eat that bar, I'm going to gain energy. If I do work, I'm going to lose energy. Energy is always positive. Like say, for example, $20, you know, if you have $20, you can either give it or you could receive it. But $20 is $20. You know, but when we give it and we receive it, there's some kind of exchange. And to keep track of that exchange, we use negative signs and positive signs. Even though, is there such thing as a negative $20? You know, like say, for example, I'm going to give you a negative $20 bill. I wish I could give you a negative $20 bill, because if I gave you a negative $20 bill, that means I received $20, positive $20, right? And you lose $20. But if I said, okay, I'm going to give you a negative $20 bill, well, you say there's no such thing. And that's true. There is no such thing as a negative $20 bill. Well, I'm going to do the same thing. I'm going to say that for methane combustion, what we're going to have here is this. We're going to have, say, CH4 plus two O2s. This is gas. This is gas. This is going to go to CO2 gas plus 2H2O liquids. And rather than writing plus energy here, I'm going to write it as delta H. Delta H is going to equal minus 890.7 kilojoules. And so what this means is that for every mole of methane that I burn, that's going to release or give away or lose 897 kilojoules. This is downhill, you know, this reaction. So this is going to go downhill by 890.7 kilojoules, basically. And so that's what the negative's saying. Now, is it possible to, let's say, is it possible, I'm going to burn some calories. I'm going to burn negative 10 calories today. There's no such thing as negative 10 calories, just like there's no such thing as negative 890.7 kilojoules. That negative just refers to the direction, you know, the direction. And so negative sign tells direction. So let's say your bank account, you saw negative $20. If you see negative $20, that doesn't mean they gave you a negative $20 bill. That means you lost positive $20. And so negative $20, you just write that, negative $20 means you lost $20. Well, negative 890.7 kilojoules means you lost 890.7 kilojoules. And so this is exothermic. You know, when we have a negative, we're losing energy. It's exothermic. When it's positive, we're gaining energy. And so if delta H is greater than 0, that just means it's positive, then it's endothermic. If delta H is less than 0, endothermic, then it's negative and it's exothermic. And so this heat of reaction is the heat of reaction here. And so we could convert all this energy into heat, and that's how much heat we get from this reaction. Or we can convert this energy into heat and work. So we aren't going to get as much heat, but we'll get some work in return, you know. And so when you burn this, like eventually I may burn this 170 calories after I eat this. And I can convert that into heat and work, you know. But that's the heat of reaction, you know, that I get from this bar here. Except this is food calories. So that would be 170,000 chemical calories, or 170 kcals. Okay. So we can do energy stoichiometry. Like, for example, if I burn 2 pounds of methane, I'm going to have twice as much heat. 3 pounds of methane is going to give me 3 times as much heat. You know, but I can do it in different ways, you know, like whatever. This is stoichiometry. And so energy is associated with all the quantities. Now, energy in conversion factors is going to be like this. I have the balanced chemical equation. So when I look at this thing, energy here, when I look at this thing, oops, here, energy. I can relate that to moles, energy to moles using the balanced chemical equation. And so here, if I look here, CH4 plus 2 O2s, this is going to yield CO2 plus 2 H2Os plus 2 H2Os, something like that. Now, the state makes a big difference. We always have to put the state. For example, if this is gaseous, we're going to get a different amount of energy. If this were solid CO2, I'll get a different amount of energy. And so states are very important in energy stoichiometry. But anyway, if I see delta H, this is a standard way it's written. The delta H is going to be minus 890.7 kilojoules here. That's the standard way it's written. Now, the relationships are here. This is if I burn 1 mole of methane, I'm going to get that much. And so this means I get 890.7 kilojoules lost. If I write lost here, that's equivalent to writing negative in the front. And so I'm going to write plus 890.7 kilojoules lost for every 1 mole of methane that's combusted. Or I could say 890.7 kilojoules lost per 2 moles of oxygen, 2 moles of oxygen, or 890.7 kilojoules for every 1 mole of CO2 here, or 890.7 kilojoules for every 2 moles of water. And so this energy is associated with the ratios here, 1 to 2, 1 to 2 ratio, mole ratio. And so I could just do these mole ratios here with energy, or flip it over, or invert, And so I can convert from energy to moles by inverting these, or I can convert moles to energy by using these straight out, like that. And so let's do a calculation here. Let's compare this bar. How much does this bar weigh? This bar weighs 40 grams. And so 40 grams of this bar yields 170,000 chemical calories. That's 40 grams. I wonder how much energy does 40 grams of methane yield? And so let's try that. I'm going to try 40 grams of methane. If I combust this, the question is, how many calories would I get? These are food calories here. Unfortunately, methane's not a food. Not a food. But it is, foods are fuels, right? But methane is a fuel. We just can't use it to power our bodies, unfortunately. The problem is we can't digest it. If we could digest it, methane would be an excellent fuel. But we don't have the, what they're called enzymes. We need enzymes to digest the food. We don't have enzymes. If we did have the enzymes to break down methane, then it would be a good fuel. I'm kind of curious what eats methane? And so let me go back here. Let me do something here. Methane-eating microbes, methane-eating plants, methane-eating creatures. I wonder if they're methane-eating creatures, what methane-eating creatures there are. Methanotrophs. Methanotrophs, sometimes called methanophiles, are prokaryotes that metabolize methane as their source of carbon and energy. Okay, bacteria. Okay, there's something that eats methane. And so they use methane to produce carbon dioxide. That makes sense. Carbon dioxide and water. Okay. So there are things that can digest methane. And I wonder if they have the enzyme, if they study that to digest methane. Methane, not starch. We have enzymes to digest starch. Cows, buffaloes emit methane gas, the natural byproduct of digest cellulose. This actually, you know, I was kind of curious about this because, you know, methane is what they call a greenhouse gas. And they're talking about feeding cows some kind of enzyme to reduce methane output. Cows produce a lot of methane. And so feeding cows enzymes to reduce greenhouse gas emissions. Yeah, so it looks like Bayer's doing it, Bayer. Reducing livestock greenhouse gas emissions. So apparently they're feeding cows some kind of enzyme, and this enzyme helps them digest methane. To do that. It's at the printer. Is it there?
Yeah.
Okay.
Original paper.
Oh, yeah. Yeah. But I guess the enzymes are using it for energy. I don't think the cows can use it for energy. And so we couldn't use it for energy either. It'd be kind of interesting if we could eat methane, but we don't have the enzymes to eat methane or the gut bacteria. Maybe you need certain gut bacteria and evolution or whatever to do it. But, oh, you know, did you even see my screen? I guess you probably didn't see my screen. You can go back to it. Oh, I guess you did see the screen. Okay. Let me go back to the original. Also, here I have this 40 gram bar. How much energy would I have gotten from eating 40 grams of methane if I would have been able to digest it? And so let's do that calculation here and compare it to that energy bar that I just showed you there. And so we're going to do some energy stoichiometry. And so here I got 40 grams of methane. And what I want to do is I just want to convert it to moles. Stoichiometry, the heart of stoichiometry is always a mole. So it's 16.05 grams of methane is 1 mole of methane here. And so grams to moles. And then here I'm going to use this. We got the ratio earlier. That is, there's plus 890.7 kilojoules of energy lost for every mole of methane. And so this is going to give me kilojoules. Well, I don't want kilojoules. I want food calories. And so there are 1,000 joules for every kilojoule. And then there are, in 1 calorie, there is, get rid of this window here, 4.184 joules. And then for every food calorie, there's 1,000 chemical calories. All right, so let's do these calculation here. So I go 40 divided by 16.05 times 890.7 divided by 4.184. 1,000 cancels. And so if I were able to eat 40 grams of methane, I would get 530.5 calories. About 530 calories, say, something like that. Let's go 4. This is, let's do exactly 40 grams. All right, 530 calories. This bar here, these Atkins coconut bars here, chocolate coconut bar, only has 170. And so 40 grams of this bar yields a lot less energy here, only 170 calories, food calories, than if I could eat 40 grams of methane. Well, 40 grams of methane doesn't taste good. In fact, it tastes like nothing. Methane has no odor, no taste. This is why they put an odorant in methane. You know what they put in natural gas to make it stink? They put thiols in natural gas, thiols, you know, those sulfur-like alcohols. And then they really stink. So you can smell it, you know, because you don't want to have any explosions. Yeah, rotten eggs, exactly. Thiols, rotten egg odors. In fact, you know, the smelliest compounds on Earth are thiols, I think. Let me, you know, if you want some trivia, let's take a look at the smelliest compounds. I don't know how they gauge what the smelliest compound is, but they have some kind of gauge, you know. Let's clear this. I'm kind of interested in this. I used to work with thiols. Smelliest compounds in the world. Smelliest compound in the world. Now let's just try that. You know what the smelliest. How can you tell? It seems that, okay, mercaptans. Mercaptans, that's a class of compounds, so they should say smelliest compounds in the world. All chemists tend to agree that the class of molecules known as mercaptans are the smelliest compounds in existence. I used to work with mercaptans. Mercaptans is just a fancy name for sulfur-containing thiols. Earth Sky fundraiser. Okay, not today, thanks. Earth Sky. Mercaptans are thiols, by the way. Let's take a look. Oh, thioketone. Thioketones are not thiols. Thioketones are very same. The dangerous stink of the world's smelliest chemical. So I guess this is it, a thioketone. A ketone is similar, to a ketone, like aldehydes. You know, formaldehyde is really stinky. Formaldehyde has an oxygen here. It's an aldehyde, but ketones would be like acetone. Acetone is not stinky, but if you replace the oxygen with the sulfur, then I suppose it becomes very stinky. So I was talking about thiols, and thiols, I think, are, you know, when it gets this bad smelling, I think they're all pretty equivalent as far as thiol smell. Many thiols have strong odors resembling that of garlic or rotten eggs. Thiols are used as odorants to assist in detection of natural gas, which in pure form is odorless. And the smell of natural gas is due to the smell of the thiol used as an odorant. Thiols are sometimes referred to as mercaptans. So mercaptans and thiols are the same thing. Thiols look like this. They look like an alcohol, except instead of an oxygen, they have a sulfur there. And mercaptans are the stinkiest smell in the world, or those ketones here. And so, Uranus. Oh, I think these are jokes. These are the world's worst smells. These are the worst smells in the world according to science. Oh, that's interesting. Science magazine is very respectable. Rotten eggs, yes. Animal puke, yes. Bloated dead animal whale, yes. Smells can be truly awful, but somehow that doesn't slow us down when we explore the big question: which stench is objectively the most disgusting? Journal of Neuroscience, underlying molecular structure. So it's structure properties, you know, there's some kind of molecular structure that these unpleasant odors have. Okay, so we have a team from Berkeley. Heavier, more spread out molecules tend to be associated with bad smells, while lighter, more compact molecules are more pleasant. That's not always true. I worked with very small mercaptans, very small thiols, and they stunk. I'm so glad I'm out of the thiol chemistry business. You know, I'd go home with headaches all the time because of smelling thiols. All day will just give you a bad headache at the end of the day. And then I had it in my lungs. You know, I wanted to get it out of my lungs. So I would go on a treadmill and go for like 6 miles on a treadmill to just try to purge it out of my lungs, and then sweat it out because it goes everywhere. And so anyway, I stopped. It was good for health, I guess, because, you know, doing all that running and trying to sweat it all out and breathe it all out was good. But anyway, I don't. Okay. Oh, I guess this fruit. Wow, why would a fruit smell so bad? Nobody would want to eat it. Wow, evacuation of the University of Melbourne. Students feared there was a gas leak. Well, it turns out it was rotten durian fruit. Caused students to panic. How funny. A 44 odor active compounds that can smell anything, like from rotten egg to delicious caramel. How funny. Wow, that flower looks pretty nasty. Or is it? Yeah, it is. The stinking corpse lily. All right. Smelliest cheese in the world. Okay. Well, anyway, you start to think about these things when you start working with mercaptans or thiols. Yeah. You think, could anything be worse smelling than what you're working with? Turns out there isn't. You're working with the worst smelling stuff in the world, which isn't so fun. Let's see. The pros of working with some of the smelliest stuff in the world is not a lot of people want to work in there. So there's lots of opportunity for doing new things, you know, with thiols and that kind of stuff. So, you know, so yeah, you know, I'm sure everybody wants to work with the more pleasant smelling odors and that kind of stuff, but you know, those fields are crowded. So you want the more open fields of scientific research, and you can work with things that people don't necessarily like to work with. You know, like when I was at UCLA, you know, the people who were working with very reactive, you know, oxidizers and reducers, they had a lab up on the roof. Their lab was up on the roof because in case their laboratory blew up, it didn't damage, you know, any floors, you know, it just damaged the roof. And they could just isolate that off. And so they're doing there. There were some people working with high energy compounds there at UCLA when I was there. All right, so let's go on here. Now let's talk about something a little bit more complicated in terms of stoichiometry. What if we aren't dealing with pure, you know, like 1 pound of pure methane? What if we're dealing with a mixture? Well, when we're dealing with a mixture, we have to account for that. So let's take a look at some mixtures here. Mixtures mean an extra step because, you know, in other words, when we look at the stoichiometry map is going to look like this now. We'll have grams of mixture. And then what we want to do is we want to go from grams of mixture to grams of A. You know, this would be pure A. And so we need the percent composition here, percent composition by mass. If we have the percent composition by mass, then if we have 100 grams of mixture, we know how many grams of A there are. And then we could go to moles, etc. You know. Or at the end, you know, we might be at grams of B, a pure B, and we might want to know how many grams of mixture we have. And so if we have grams of mixture over here, then we'll need to know the percent composition here in order to figure it out. Now we have two different percent compositions. We have percent composition by mass. Okay. And so this would be an example of percent composition of mass. Do you know the modern day copper penny? Modern day copper penny weighs 2.5 grams. But a copper penny is not copper. A copper penny is 97.5% zinc by mass. And so copper is a piece of zinc that's, a copper penny is a piece of zinc that's coated with a very thin layer of copper. Otherwise, you know, copper is a very expensive metal. And so if they made a solid copper penny, it's worth way more than what a penny's worth. And so they use something inexpensive like zinc. And so old copper pennies, which were pure, weighed 3 grams. You know, zinc is a lot less dense. And so it's only, new copper pennies weigh 2.5 grams. And so we can do some reactions here. We can add excess HCl. When we add excess HCl, only the zinc reacts. It depends. The copper is pretty inert to HCl. You know, HCl is not going to do anything to the copper. And so there has to be a scratch, because if the copper is completely sealing the zinc, then the HCl can't attack it. So you put a scratch in there to expose some of the underlying zinc or something, and then the HCl can get in there and attack the zinc, you know. But the copper pretty much protects the underlying zinc. So we'll put a nick in the side of it, you know, scratch it on some concrete or something, a nick there. And now the zinc is exposed. Once the zinc is exposed, it can be attacked. Only the zinc reacts. There's no driving force. This is single replacement. And so if we have zinc solid, we need 2 HCl's here. And this is going to form ZnCl2. Zinc is fixed charge plus 2 plus hydrogen gas, H2 gas. Driving force here is going from, you know, more active. If we do this single replacement, more active zinc to less active hydrogen. And so this is driving force. The zinc is going to want to react. However, if we take copper and react it with HCl, 2 HCl's, because we're going to form copper 2, we should form copper 2 chloride and H2 gas. In this case, copper is less active. Zinc compared to hydrogen. Hydrogen is more active. You know, I asked you, what would you rather have in the trunk of your car, you know, or in your bedroom? Hydrogen gas or copper metal? Well, copper metal, you know, Hydrogen gas is dangerous. So this is more active here. And so here there's no reaction. We would need something, this is a mineral acid. So mineral acids work with single replacement. We would need an oxidizing acid if we want to dissolve the copper. And so like nitric acid, no problem. We use nitric acid, that'll heat up the copper and heat up the zinc. But if we use a mineral acid like HCl, the mineral acid will attack zinc, but it won't attack copper here. And so what we can do is we can figure out, you know, how many grams of hydrogen are produced, hydrogen gas are produced in this reaction. And so how many grams of hydrogen gas? Oops, didn't want to do that. Okay, so if I take 1 penny's worth of the zinc copper mixture, 2.5 grams, how many grams of hydrogen going to be produced? So I'm going to have 2.5 grams a penny. And so what does this say? This says 97.5 grams of zinc for every 100 grams of penny. And so we'll put that in here, 97.5 grams of zinc for every 100 grams of penny. And so this gives us how many grams of pure zinc we have. And then we need the molar mass of zinc. What is the molar mass of zinc? I'm gonna just look it up on my phone because I don't wanna deal with changing the page on the computer. So it's like 63, but let me just look at it. By the way, zinc, they say, is important. There's one more supplement that a lot of the medical professionals that I watch take, and that is vitamin C with zinc. You know, zinc is important in superoxide dismutase. Superoxide dismutase helps break down superoxide, you know, to protect you. And zinc is also important in membrane transport, you know. And so like for example, hydroxychloroquine with zinc is much more effective than hydroxychloroquine alone, that kind of thing. Oh, I was 65.38. And so 1 mole of zinc, 65.38 grams. Usually, the zinc is going to be in the form of Zn2+, so zinc ion. Now, we don't make the differentiation. Whether it's zinc ion or zinc metal, we use the same molar mass, the same atomic mass. And technically, they're slightly different because zinc ion is missing 2 electrons. 2 electrons are not weightless. 2 electrons do have weight. And so there's a little bit of error associated with that, but we usually ignore it. I don't know why. I think the reason why is it's too much hassle to recalculate all the molar masses. And then what they do is, you know, compounds are neutral. So, you know, if something loses 2, something else gained 2, and it kind of works out in the end. All right, then we saw from the balanced chemical equation that there's 2 moles of, is there 2 moles? No, there's 1 mole of hydrogen per 1 mole of zinc. Let me do that here. Going to be 1 mole of hydrogen for every 1 mole of zinc. And then hydrogen I usually use 101, you know, as its mass. But here, since it's alone as an element, I have to use 1008. Otherwise, I'm not going to get 4 sig figs. And so I have two of them. It's going to be 2016, 2.016 grams of H2 per mole of H2. And so let's go. So we have 2.5 grams of mixture. So 2.5 and then times 97.5 divided by 100 divided by 65.38 times 2.016. All right, so how many grams of hydrogen do we produce? So not that many, 0.07516. This is because hydrogen doesn't weigh much, 0.07516 grams. We only allowed 2 sig figs, and so this is 75 milligrams of hydrogen gas produced. Okay, so that's a mixture, so we do one extra step. This is going backwards. Determine the percent composition of a penny. So let's say this is just going backwards. Okay, the percent composition, let's say we're going to get the percent zinc. Percent zinc is going to equal the mass of zinc divided by the mass of the penny. And so the information, we have to be given certain information. And the information that's going to be given here is 2.5 grams of mixture, the penny. Of course, we have to have the zinc exposed because if the copper is completely enclosing the zinc. This is why it's bad to eat pennies. Little kids eat pennies. When little kids eat pennies, they get zinc poisoning because their stomach acid will start to attack the zinc. The zinc will be oxidized to zinc ion. The zinc ion is going to cause trouble. And so kids aren't supposed to eat pennies. Now, if the penny were completely covered, like new pennies, then probably nothing's going to happen, because the copper is going to protect the zinc and the zinc won't be exposed to acid. And the copper is not going to be attacked by the acid. And so that's all right. So we got 2.5 grams of penny. Unless, sometimes copper gets oxidized and the oxide coating on pennies gets attacked by acid, But these are brand new pennies, not, oxidized pennies. If it's oxidized pennies, then acid will attack the oxide in the double replacement reaction. And so here, let me shut the door here. Okay, so, oxides like copper, if your penny's quite black like this with copper 2 oxide coating, then HCl can eat up the coating. This is just double replacement. So if HCl eats up the coating, we get copper 2 chloride and water, HCl liquid. And so we're going from stronger acid to weaker acid. So if your penny is coated with oxide, the acid will attack the oxide, the mineral acid will attack the oxide and dissolve it. And that'll expose fresh copper underneath it. But the fresh copper that's underneath, copper with HCl yields no reaction in it's a mineral acid. So mineral acids obey single replacement. If it's an oxidizing acid, then we definitely need to use the chart method. We could use the chart method for this as well. I didn't because it just takes a little bit more time. And so we're given 2.5 grams of penny, and let's say we're given that and 75.16 milligrams of hydrogen is produced upon reaction with HCl. Reaction with HCl. And so here we're given what happened here. We took the penny, put in HCl, and we got 75.16 milligrams of H2. Now we have to know that all the H2 came from zinc. none of the H2 came from copper. And so all H2 comes from zinc. Reaction with zinc comes from reaction with zinc. And so we generate the equations that I generated earlier that I had erased. And we're going to do this from stoichiometry. And so this is stoichiometry in the top, stoichiometry. And on the bottom, this is given. So we could do this in one equation here. If we want the mass of zinc, we're starting with the mass of hydrogen. And so we start off with the mass of hydrogen and figure out stoichiometrically, this is milligrams, not grams, of hydrogen, how many grams of zinc. And so if that's the number of milligrams, then we know that for every 1 gram, we have 1,000 milligrams. And so that converts milligrams into grams of hydrogen. And then we go to moles. And so 1 mole of hydrogen, H2, weighs 2.016 grams. And so that takes us to moles of hydrogen. Then we go from moles of hydrogen to moles of zinc. And it turns out there's 1 mole of zinc for every 1 mole of hydrogen. And so that takes us to moles of zinc. And then we go to grams of zinc. Zinc, 65.38 grams of zinc, 65.38 grams of zinc per mole of zinc. And so finally I have the grams of zinc on the top, and that's what I want. I want the grams of zinc on the top, and then on the bottom I'm going to have grams of penny. Well, it's a 2.5 gram penny. And then I have to multiply by 100%. I forgot to add that in here, so I'm going to add that, tack that in at the end, times 100% to convert it, a fraction, into a percent. We can convert any fraction into a percent by multiplying by 100%. And so we'll do the calculation here. So I'll start off 75.16 milligrams of hydrogen divided by 1,000 divided by 2.016 times 65.38. All right, so that I get 2.43. And so out of this 2.5 gram penny, 2.437 grams of that is zinc. And so 2.437 grams of zinc for every 2.5 gram penny. So it's mostly zinc, and then times 100%. So we have the, here we have the fraction of zinc in the penny. And so divided by 2.5 times 100 gives me 97.499% zinc. Okay, minus 100, that gives me 2.5007% copper. So it's about 2.5% copper, 97.5% zinc. That's what a penny is by mass. So we have both types of problems, you know. Sometimes we're just given this, determine the percent composition. When we determine the percent composition, we come up with an equation like this. Here. Or sometimes we have a problem like this in terms of mixtures. Okay, we also have mixtures by mole. And this is going to be, for gases, let me write something here. For gases, percent by mole is equal to percent by volume, which is not equal to percent by mass. Okay, there's one more thing for gases, and I forgot to write that, is the percent by pressure, P. And so sometimes we have mole percents. For example, air. Air is 21% by mole O2. 21% mole by O2 means this. It means 21 out of 100 parts. Now the parts are moles, volume, or pressure. And so this is 21 moles of O2 per 100 moles of air, which is equivalent to 21 liters of O2 for every 100 liters of air. We're going to talk about this later, which is equal to 21 atmospheres of O2 for every 100 atmospheres of air. And so the percentage is the same whether we're using mole, liters, or atmospheres, or bars, or whatever units you want. You know, you could use different units as long as they're volume and pressure units. And so, so what we're going to do is, actually, what should we do? I think we did the molar mass of air. Yeah, I think I did the molar mass of air before. And so, how many grams of air? How many grams of air are there? Are required? How many grams of air are required to burn 1 pound of methane? Actually, I don't want grams. I want how many pounds of air. How many pounds of air are required to burn 1 pound of methane? Okay, so let's try to figure this out. Now, so I have 1 pound of air. Or no, 1 pound of methane. 1 pound of methane. And so I'm just going to do stoichiometry here. Let's go pounds to grams. 453.6 grams per pound. So we got grams of air, methane, excuse me, grams of methane. And then we're going to go to moles of methane. And so 1 mole of methane weighs 16.05 grams. So that takes us to moles of methane. Moles of methane will go to moles of oxygen. So based on the chemical equation, there's 2 moles of oxygen for every 1 mole of methane. But we don't have oxygen. Air is not pure oxygen. Air is 21% oxygen. So that means we'll need 100 moles of air for every 21 moles of oxygen. And that's how we're going to use the percent there. Now we have 100 moles of air. Well, how much does a mole of air weigh? How much does a mole of air weigh? Okay, this calculation is similar to isotopes. Okay, there's 21 out of 100 parts of oxygen, moles. And the molar mass of oxygen is 32.00 grams. And then the rest is, let's say, nitrogen. So air is more complex, but we're just going to say 79. Yeah, 79 parts out of 100 are nitrogen by mole. And the molar mass is of nitrogen, N2 is 1401 times 2 is 28.02 grams. This is grams per mole, grams per mole. This is moles, and cancels kind of thing. Or we could leave it grams per mole, grams per mole. And so what does that make that? And so I'm going to do 21 divided by 100 times 32, 6.72 plus parentheses 79 divided by 100. times 2802, close parentheses. I've got 2885. This is the weighted average molar mass of air. And so it's going to be closer to nitrogen. You know, take a look. Nitrogen is 28, oxygen is 32. If it were 100% oxygen, it'd be 32. If it were 100% nitrogen, it'd be 28. It's 80%, so it's closer to nitrogen. Do you see that? And so this is the molar mass. Actually, let me use molar mass units, grams per mole, grams per mole. This is the mole ratio, not the mass ratio, the mole ratio there. And so this is what we got here, 28.855 grams per mole. So that's what we're going to use here. You know, air weighs about, if I had a mole of air, 6.022 times 10 to the 23rd air molecules, most of those molecules, 80% of those molecules are going to weigh this much. 20% of the molecules are going to weigh this much. So the weighted average is 28.855 grams of air for every 1 mole of air here. And so this should tell me how many grams of air, but I don't want grams, I want pounds. So let's convert it to pounds. A pound is 453.6 grams. All right, so let's go ahead and do the calculation here. Calculation is going to be 453.6 cancels out. So I'm going to get 2 times 100, 2 times 100 times 28.855, 28.855. All right, then that's going to be divided by 1605, 16.05 divided by 21. Okay, and I end up with 17.12 pounds of air. Remember, we only needed 4 pounds of oxygen, but we're going to need 17 pounds of air because air only has 20% oxygen in it, or 21% oxygen. And so 17 pounds of air. All right, so this is a mixture type stoichiometry problem using moles. All right, that's the end of chapter 10. I forgot to make the PowerPoints for chapter 11, but I'll talk about chapter 11, but first we're going to look at problems from the book. And so I'm going to look at problems. From the book. Oh, here it is. I got logged out. Well, you know what? It's time for a break, isn't it? So, okay, it's time for the next break. Let's take a break again, and then we'll meet back in 15 minutes. Okay. So I'm going to stop the recording.